When it gets allocated, the pointer that you're looking at, or the pointer that gets returned to you by malloc, points in the metadata on the instance that's in the heap or in the free list still. Traditional exploitation of it used the unlink macro, just like pretty much everything out there dealing with the heap. It was created by Solar Designer, or found by Solar Designer in a JPEG bug in Netscape. Back then, that's basically what it looked like. We just took the 2 pointers and dereferenced the pointer to the pointer, and overwrote an arbitrary memory address with 5 or 4 bytes of our choice, or size of a pointer of our choice. So in the process of doing a traditional exploitation, you just had to get the same block freed twice, get 1 block allocated back to you, overwrite the forward and the back pointers, or maybe even one of them depending on the instance, allocate the second instance of the block on the free list, and so when it actually gets unlinked, you would perform that overwrite. It's actually kind of the same thing as traditional buffer overflow, except instead of trying to call free after you've overflown, you're calling malloc to get it back. It's pretty good. It worked, but like all things, it kind of ended. It's been hardened pretty much everywhere, and then on top of it, double freeze protections have been implemented in a lot of different places. The new unlinked macro specifically checks the sanity of the lists to make sure that what they point to is what's actually being freed. And this is by and large the result of people actively exploiting it. In a specific example, what we're talking about is a couple of multiple free conditions that were found in Modoth Kerberos versions 5.2, 5.3. Pretty much everyone that I looked at, but I didn't go digging too deep. The bug itself probably isn't that big of a deal. Getting a reliable exploit off of it has been non-trivial. And on top of that, the section of code it only gets compiled conditionally. So not everybody is going to be even using this piece of code. In fact, a lot of people are not going to be using it. Interestingly enough, it looks like it came from an old version of ASN1 compiler out of Heimdall. Newer versions don't have the same problem, but they have a lot of other problems. The code that gets generated from your .asn1 files, if you're using it, you should really take a look at that code, because it's got a lot of problems, and it's kind of one of those things that you have to expect to have problems. It's program reading code and generating code off of that. Initially, I had a lot of code in here, and it was kind of hard to represent in slides, so I opted for diagrams instead. I apologize to everybody that would prefer to see code. I would have preferred to see code, but it just wasn't working. So in the first vulnerability, what we have is that the function decode neg token init calls down into decode mech type list, which in turn calls decode mech type. And if any of these functions error out, then they call their free function, which for decode neg token init is the free neg token init, and for free mech type list it's free mech type, or excuse me, for decode mech type list it's free mech type list, and which in turn free mech type list is also called by free neg token init, and they both call free data to val. The second one's a little bit more complicated. It's the same code path: decode mech type list, decode mech type, decode OID, and dir get OID. And in turn, the problem occurs again that essentially they have wrapped or nested error handling functions that all propagate the error back up, and they all free the same memory. In this instance, it's the component structure, or the components element of a structure, and this one's actually directly user controlled. Earlier versions of glibc had no thread safety. They're still listed as being not async safe. And looking at it and trying to deliver signals, I found that you couldn't really do a whole lot with it. So whether it's asynchronous or not is quite possibly debatable. But the lack of thread safety was originally demonstrated in delivering signals for fun and profit, which was a pretty good paper that a lot of people don't seem to be aware of, and they haven't actually. It's fairly underappreciated. Thread safety is a key difference between Douglas malloc and PT malloc, and it's provided by two mutual exclusions in the code base. One is by the list lock mutex, which is locked when mostly when causing or creating a new heap or arena, and the reason it's used is just because the per arena mutex may not have been acquired, and that may be why we're creating the new heap in the first place. In that it effectively blocks two threads from entering the same code or entering critical sections at the same time, and does a fairly good job of that, obviously. However, the code base itself is written in a manner that's it's only meant to be executed in a linear fashion, and the mutexes are good. They work, they keep you from getting in there at the same time, but it doesn't stop someone from creatively using threads, or using the threads to creatively take the sequence of events out of order. A lot of those assumptions as far as the linear execution of the program are actually found in the double free protections. However, I don't really fault the glibc developers if you can't really say, no matter how many protections they put in there, if you have a buffer overflow in your code, they can only do so much to protect you from messing yourself up. Same thing applies to double frees. The double free protections and normal size chunks. The first check that it does is it checks to make sure that the chunk being currently freed is not the top chunk for the arena. Not really a problem. Most of the time, what you'll most likely encounter is that there's already been other chunks that have been allocated, so you're not next to free in the first place. Where I did run into issues with this is where I had a test program that only had my allocations, and then I kind of ran into problems. I don't think I've ever tripped this one though, so it really wasn't even something I had to deal with a whole lot. The next check first checks that the arena is contiguous, and then it checks to make sure that the next chunk is not outside the bounds of the arena. One obvious way to bypass that is to make the chunk the arena non-contiguous. I found that it was actually kind of hard to just create that or to cause that condition. You could do it, but when I did tests on it, I think it took something like 100 threads allocating large amounts of memory and not freeing it to actually create a new arena. But when it did happen, every single time that I tested it, it actually resulted in a non-contiguous heap. Nonetheless, doing that really, it messes with the state of the heap, and it makes it more complex, and we're already kind of dealing with a complex issue in a very small time frame, so the more complexity we can take out of it, the better off we're actually going to be. And again, I never even ran into that instance. It's going to be something more along the lines for buffer overflow that check actually is going to occur. The last check in the normal size freeze, however, or normal size chunks, there's really no way around it in a linear sense. And all the other ones, you could manipulate the layout of the heap to be able to bypass them. However, this one checks to make sure that the next chunk actually lists that the chunk prior, or the chunk currently being freed, is currently in use. However, this is where threads come into play, because of the fact that you can have two threads and have this data structure shared between them. You can actually cause a free, then cause a free in one thread, allocation in the other thread of the same size. Exploit the fact that you get the LIFO, exploit the LIFO manner of it and get the same chunk back, and then have the other double free occur. When that happens, you actually bypass all of these checks, because to libc, it's not actually a double free. The chunk is actually allocated. However, when the chunk that allocated it back goes to do something with it, it's going to invalid reference to the heap. So it's kind of a buffer overflow, but without the buffer. Fast bin chunks are much better. They sacrifice a lot of things in the name of speed, and unfortunately one of them is the security of the double free protections. The only relevant check is that the bin index for that chunk is not equal to the current chunk. And what happens when you free it and it gets put onto the list, it ends up as being the top chunk in the index. So this check right there just checks to make sure that the chunk being freed right now is not the same chunk that was freed most recently. In this, we have a reliable method for causing a multiple free condition. If we can get another chunk in the same bin freed prior to that second or multiple free, then this check is easily bypassed. So, taking what we know and applying it, if we want to exploit a normal sized chunk, we can't get colorless with the top chunk. If the chunk plus its size cannot be outside the bounds of the heap, or the heap needs to be non-contiguous. And then in the next chunk, the previous in use bit must be set. Fast bin chunks, like I said, it's very trivial to bypass. All you need is free pointer 0, free pointer 1, free pointer 0, and you get past it. I apologize for that. Well, you can't see it very well, but in the control flow of this, or the entire function, or the entire control flow down to the vulnerability, is that we enter in through a function called authenticate user GSS, which calls some internal Apache API calls to get the length of the base 64 string, allocate memory based off of it, then decode it, and in turn calls GSS accept sec context sp nego, which then in turn calls the decode neg token init and all the way down the chain. So in the first method for exploiting these vulnerabilities, using the second vulnerability and doing it with fast bins, under this specific instance, and again this is where the code probably would have helped you to understand a little bit more. It wasn't exploitable. What you get to write with is an unsigned integer, and because it's what is decoding at that point in time, the first 8 bytes, the first one gets divided by 40, and then the second one gets modded by 40. So you have a very limited subset of what you can actually write, and as a result of that, the pointers, there's just nothing you can do with it unless you can get an address at 40 or something. However, it doesn't invalidate the techniques. It just invalidates them in this specific instance. You're not taking control directly via the linked list operations. You are taking advantage of it, but you're not doing anything like exploiting the unlink macro or similar. What we're actually going to do is cause consolidation to happen and use consolidation to take control. So what we need to have occur is that we need to get 2 chunks of the same size that are within the fast bin chunk range freed, and we need to get them freed interchangeably. So free A, free B, free A, free B, and we can go on that indefinitely unless we cause, in doing so, we screw